This lecture is on one of the important models of all times, well, according to my personal rating, of course. It's about logistic regression. Um, yes, it took me some time to put a lecture together, so all the bits and pieces are clear. But here we are. In order to understand logistic regression, well, at least to understand it the way I see it, I think we need to take a slightly closer look or a different look at naive Bayes, which you all are professional in right now. And then we need to define logistic regression and then solve it. Usual, easy. Define and then solve. Let's go. Let's start with the naive Bayes. As you remember, naive Bayes comes with the following assumptions that drag in the following properties. The assumptions are the following. Features xi and xj are conditionally independent given the class label y. For a two-class example on the slides here, if we only have, two feature example, not two class, xi and xj, the joint conditional factors into the marginal conditions. So features are conditionally independent. Sorry, just reminding you from the previous lecture, you all remember that quite vividly, I assume. But that's the major assumption. So, for example, feature of email coming or spam coming in the morning or in the evening at a certain date time is independent of the presence of word luxury in that email as another feature in the spam email. Given the class, right? The same class. In a slightly more general term, what we mean is for all of the features, the joint distribution of all of the features given class or class conditional joint distribution factors into a product of class conditional feature distribution per individual feature, the ith feature. Yeah. Okay. And decision boundary, or the process of this, not decision boundary, but the process of deciding the algorithm for naive Bayes is just to pick that class that maximizes the posterior, or product of the likelihood and the prior. This is the class prior for all of the y's. Look through all of the y's and compute the posterior probability of this particular class given the data. Blah blah. Well, you know. And pick the y that gives maximum for this value. That's how naive Bayes operates. But what is that? And what is that? Well, just assume some parametric form for the conditional and for the likelihood and for the prior. Easy. Just a reminder, just to recall how, but another point is, well, you assume the parametric form, but parametric form means that there are some parameters here, some parameters there. What do you do with them when all you got is data? Remember, our data set is that set that I was just writing. Set of ensamples. Well, you just estimate maximum likelihood, use maximum likelihood to estimate parameters for these functions, these parametric forms for the likelihood and the prior and then just plug in those MLE estimates and operate the naive Bayes classifier by this formula. Okay, are you comfortable with that? Recalling where that's coming from and how that works? Great. Let's go a little further. Gaussian naive Bayes. Gaussian naive Bayes is when we assume Gaussian parametric form for the likelihood. This is our likelihood, and we're saying that, well, assume that given the class Y, our distribution of xi feature I is just this one-dimensional Gaussian. It has class-specific variance and, of course, class-specific and feature-specific mean. Additionally, we will assume that the class prior is just Bernoulli. So with probability pi for two-class Bernoulli, of course, but for multi-class we can use directly multinomial, not directly. Directly is just the conjugate for the multinomial, but let's not complicate things. Bernoulli, two classes, pi, that probability of pi that y equals 0, probability of 1 minus pi that y equals 1. The usual. We can have as well, we should have, otherwise it will be harder to distinguish different means for each class and each feature, and also different mean and different variance for each class and each feature. Okay, that should be clear, right? The usual Gaussian, the Gaussian distribution for one-dimensional variable. And what are my notes here? But let's assume now that variances are independent of the class. So variance is just a feature specific. It doesn't matter which class the feature belongs to. What that means graphically is that, say, each feature, say feature I, okay, that's so inventive. Yeah, feature I for class 1, it's one Gaussian, and for class 0, it's another Gaussian. So the sigmas should be the same, and the only difference is in the means, in the mean location. So let's make that assumption for simplicity. That will be useful for us. Repeating, just so you see it on the slide. Likelihood is one-dimensional Gaussian, but now the features for two-class problem, or the variances for two-class problem are the same for each class. What can happen? Well, what is decision boundary? The decision boundary for this problem is, or for any absolute problem, is the set of points at which posterior for one class or for all classes is equal. Posterior distributions for all classes are equal. For the two classes, this is posterior distribution for class 0, and this is posterior distribution for class 1. Or in our form, the way we decided to write posterior distribution and to model it is the likelihood times prior. Thanks to Bayes, there are normalization constants, but they don't matter, they cancel out. So the decision boundaries were they equal. Remember, we had one-dimensional case, okay, they're equal here. This is decision boundary, one class, another class. In two-dimensional case, this boundary could be more interesting, could be less interesting, we'll see. And in this case, equivalently, this equality I can write just as the ratio. Well, when they're equal, the ratio is 1. That means the log ratio is 0. So I can decide which class my sample belongs to by looking at the log ratio of posteriors, and if it is greater than 1, then it's class 0. If it is less than 1, then it is class 1. Greater than 0 respectively for the log ratio, and less than 0 respectively for the log ratio as well. So, but now let's take our Gaussian distributions for the likelihood and our Bernoulli distributions for the priors and plug them into this log ratio that encodes our decision boundary. Immediately the priors fall out. This is the log of our priors, log ratio, and we have a sum of log of ratio of probability likelihoods. So this is called likelihood ratio. Let's see what happens next. Okay, this is a little bit more interesting or clearer form. Now, if we follow through with the algebra and plug in the actual parametric form of our likelihoods for class 0 and class 1, specifically relying on the fact that the variances are the same for or class independent, then after doing the algebra, we'll get the following. This is our priors, Bernoulli. This term falls out and it doesn't depend on the data. It just depends on those intrinsic parameters of the likelihood distribution. That which shows us that this is a constant term independent of the independent of the data, and only this part multiplicatively affects the data. If we combine this constant into a single constant here, we'll see that, oh, look, what we are getting bias plus linear term. Gaussian naive Bayes in the case of the same variances or class independent variances is a linear classifier. The decision boundary of this Gaussian of the Gaussian naive Bayes in this case, in the assumption of sigmas to only dependent feature, no dependent class, is a linear function. So when it's 0, it's right at decision boundary. When it's above 0, positive class. When it's below 0, negative class. And you can relate this now back to your perceptron homework question and everything that you learned about perceptron in the previous lectures. Or perceptron was our simplest model of a linear classifier. Okay, let's go next. Generative classifiers versus discriminative classifiers. Now we're ready to talk about it. Generative classifiers, and naive Bayes is one of them, examples of such classifiers. They assume a functional form for the joint distribution of data and the labels, or equivalently functional form of likelihood and prior times the likelihood. It's the joint. If we don't normalize it by the evidence, but okay. Well, then we estimate those generative classifiers. Do we estimate parameters? Well, because we assume the functional form, we have parameters, they're different. This is just a placeholder theta for the corresponding parameters of those distributions. Now we can estimate parameters of the likelihood and the prior from the training data. And after doing so, not only generative classifiers can classify the data into classes that they were trained on, but they also are able to generate samples from trained model, because we can randomly sample from this distribution first, which class it is, then plug this class into the likelihood and sample the data according to the distribution given the class that we have just sampled. So this is our generative process. We kind of assuming what in the world, how the world operates to generate the data we have collected, be it samples of a missed handwritten digits data set or coin tosses or whatnot, generative classifiers. And note that argmax of prior times likelihood is the same. The y that maximizes prior times likelihood is the same y, the same class that maximizes posterior distribution of data of the class given the data. So why don't we learn instead the posterior distribution directly rather than learning prior and likelihoods separately? So why don't we learn the decision boundary directly? Because posterior distribution basically is our step towards the decision boundary. So why don't we learn decision boundary directly, as we used to do with perceptron? Remember, perceptron was learning decision boundary directly, but perceptron didn't assume any kind of probabilistic model behind the process, while generative distributions and naive Bayes assumes makes those assumptions. So can we stay within an interesting probabilistic framework and still learn the decision boundary directly? This will be discovered or uncovered in the next episode.